Good evening friends. Today I am going to discuss about the topics counters in digital electronics. What is a counter? A counter is a circuit which is used for counting the pulses. Here we are having any number of pulses like 0, 1, 2, 3, 4, or I want to count the number of students who are entering into a class. So I can apply a counter at that point. So here the counter can be of two types, asynchronous counters and synchronous counters. What are asynchronous counters? In case of asynchronous, all the flip-flops are not connected simultaneously. Like I will be applying the clock pulse to the first flip-flop, then the output will be obtained from the first flip-flop which is applied at the input of the clock for the second flip-flop, and the output of the second flip-flop will be applied as the clock for the third one. In case of synchronous counter, all the flip-flops are clocked simultaneously, means we are applying the clock at the same time to all the flip-flops and all the outputs will be obtained at a single clock pulse. Now in this lecture I will be going to discuss about synchronous counter, like what is synchronous counter and how to design a synchronous counter. The first thing is the advantage. Like I have told you that all the flip-flops are clocked simultaneously, so the speed of operation improves. Second is it can be designed for any count sequence. Like if I want to count 1, then 3, 5, 7, or I want to calculate count the sequence like 8, 10, 16, 21, then I will be applying those sequences only, and then I will be making a counter. Now the design steps. The design steps consists of the first one. So first thing is we will have to find the number of flip-flops required. If I want to design a 3-bit counter, so I will be requiring 3 flip-flops, as I have told you earlier also that one flip-flop will be using 1-bit memory, or it will be representing a 1-bit data. Then I will be writing down the count sequence, means what is the input count sequence I have to give. If I want to give a up counter, or if I want to design a up counter, in that case I will be using 000, 001, 010 up to the last one. Similarly, if I want to design a down counter, so I will be using 111, then 110, 101 and so on. So this is how I will be writing down the count sequence. Then I will be determining the flip-flop inputs which must be present for the desired next state from the present state using the excitation table. As we have done in case of conversion of flip-flops from one type to another type, similar to that, here also we will be having the present state and the next state. And from those two states, I will be finding out the inputs for JK flip-flop. These inputs can be anything that will be depending on the present state or the excitation table of that flip-flop. Then once I will be having the inputs, after that I will be preparing the K-map and I will obtain the logic equations for inputs, and then finally I will be drawing the circuit which will be consisting of the number of flip-flops with clock applied to all the flip-flops simultaneously, and inputs will be depending on the circuit. Now I am considering the first example, which is the design of 3-bit synchronous counter. First thing is I am using an up counter, or I am designing an up counter. An up counter is starting a sequence from 000, as you can see here, and it will be, the last sequence will be 111, and once 111 will be obtained, the next sequence will always be 000. So here I have written the truth table 000, 001, 010, 011 up to 111, and after 111, if I am applying the next clock pulse, I will be getting 000. Now as per the design steps, the first thing is the number of flip-flops required. As I am designing a 3-bit counter, so it will be requiring 3 flip-flops, and the 3 flip-flops will be having 3 inputs. That will be J0 K0 to the first flip-flop, J1 K1 to the second flip-flop, and J2 K2 to the second flip-flop. Now how to design the flip-flop? For that, here you can see for Q0 I am having for present state as 0 and the next state is considered as 1. So in case of the excitation for JK flip-flop, you can see for 00 I will be getting 0 cross, don't care. For 0 1 it will be 1 don't care. For 1 1 0 it is don't care 1. And for 1 1 means if there is present state is 1 and the next state is 1, I will be getting don't care 0. So for the case of Q0, it will be moving from 0 to 1 or 1 to 0, and in that case I will be getting the inputs of J and K to be 1 cross 1 don't care, as you can see here, 1 don't care or don't care 1. So similar to this, I have made the inputs for J0 and K0. Here Q0 is 0, that is present state is 0 and the next state is 1. So whenever we are having the present state as 0 and the next state as 1, it will be 1 cross or don't care. Next is 1 to 0, so it will be don't care 1. Then 0 to 1, 1 to 0, 0 to 1, then 1 to 0, 0 to 1, and finally 1 to 0. So depending on the excitation table, we will be giving the inputs for J0 and K0 depending on Q0 only. That is, if Q0 is changing from 0 to 1, I will be getting 1 don't care. When it is changing from 1 to 0, it will be don't care 1, and similar to the next one. Then I will be making the inputs for J1 and K1. For J1 and K1 as inputs, I will be considering Q1. That is, it will be having the present state as 0, next state is 0. Then present state is 0, next state is 1, as shown by the arrows. Then 1 to 1, 1 to 0, 0 to 0, 0 to 1, 1 to 1, and finally last one is 1 to 0. And depending on this, I am getting J1 and K1. Like if the present state is 0 and the next state is 0, I will be getting 0 don't care. For 0 to 1, I will be getting 1 don't care. For 1 to 1, I am using don't care 0. Then 1 to 0, I am getting don't care 1. These inputs are written with the help of excitation table, and this Q1, it is using the present state, next state, present state, next state, as shown in arrows. So this is how I will be making the inputs for J1 and K1. The third is Q2. That depending on this Q2, I am having the inputs as J2 and K2. For J2 and K2, to find out the inputs, I am using for present state is 0, next state is 0. Again present state is 0, next state is 0. Present state is 0, next state is 0. Then 0 to 1, present state 0, next state 1, and so on. And depending on this, I will be getting J2 K2. If 0 to 0, 0 don't care. Then again 0 to 0, 0 don't care. 0 to 0, 0 don't care. Then 0 to 1, 1 don't care. And similar to this, I am filling all other inputs. So I am getting the outputs J0, K0, which will be acting as inputs depending on Q2, Q1 and Q0. Similarly, I will be getting J1, K1, and I will be getting J2, K2. So this is how we have made the third step, that is determine the flip-flop inputs which must be present for getting the next state from the present state. Now the next step will be to prepare the K-map and obtain the logic equation. So what we have done is we have started with J0, and the inputs to the K-map will be Q2, Q1 and Q0, and I will be filling all the values of J0. Then I will be making the second K-map for K0, then the third one for J1, K1, J2 and K2. After making all the K-maps, I will be simplifying them, and from there I will be getting the equations for J0, K0, J1, K1 as shown here. J0, K0, J1, K1, then it will be for J2, K2. As you can see, for the case of J1, J0, it will be Q2, Q1 and Q0. I have filled the values, and because all the values are either 1 or don't care, so it will be making a pair of 8. So all the values are considered to be 1, and the value of J0 will be 1. Similar is the case for K0. K0 will also be 1. For the case of J1, as I filled it, in this case, the above two don't cares are not used, and the remaining 4 values, 1, don't care and 1, it will be forming a pattern, and J1 will be equal to Q0, Similarly, K1 will be equal to Q0, then J2 is equal to Q1 into Q0, and K2 is equal to Q1 into Q0. Now, as we have to design 3-bit synchronous counter, which is up counter, so I have applied the clock. As you can see, we are using 3 flip-flops, J0 K with inputs J0 K0, with inputs J1 K1 and inputs J2 K2, and we are applying the clock simultaneously to all the 3 flip-flops. Now, as I have done, J0 is 1 and K0 is 1, so we have applied 1 to both J0 and K0. In the second case, for J1, J1 is equal to Q0 as we have done above. So Q0 is directly connected to J1, and also K1 is equal to Q0. So K1 is also directly connected to Q0. Then we have obtained Q1, and for J2 it is Q1 into Q0. So we have used an AND gate which is having the inputs as Q1 and Q0, and this output is going to J2 and K2 to get the final output as Q2. So this is how we design any counter, synchronous counter with the help of excitation table. Thank you.